I have 7:30. This one is expected to take, of course, not all of the time to so get started. And again, we are still working on this part of the case study of MIPS. I'm going to finish the instruction formats with going over load word, store word, and jump. And we'll also go through some examples, branching and the immediate field of the branching. And then on Friday, we'll cover this, but after today, you should be able to finish homework. So I will update the due date to reflect the due date that I put on Canvas. So I'll update Gradescope today, but it should be Friday next week. So we have these I-type formats. Right, and we just have two registers and then the 16-bit immediate. So this immediate range between -2 to the 15 to 2 to the 15 minus 1, because it is a signed immediate. That's why we have 15 and not 16. Right. So here's our example that we've seen similar ones before, right? We want to add some variable to some data in memory. First thing that we have to do is load word. This is our offsets, 300 times 4, right? Because one element is a word, and our base address is 3. So that gives us the address of the data in the array A of the 300th element. Add to that data the variable h, and then store it back to that same address. Right? So here's the machine code. Have the opcode field that tells us that it's a load word. This is our RS, which is the base address, RT, which is our destination, and this is our offsets. Again, we have add, so opcode for R type is 0, and then the funct code down here tells us it's an add. RS, RT, RD, and we don't use shan't, which is shift, because we're not a shift. And then store word, very similar opcode to load word, and the format is the same. So, and we have same base address, same offsets, and our destination isn't really a destination. This is the register that we want to copy the data from and store to memory. Okay. So the other format are these J-type, which are for jumps. So the opcode is to tell us that it's a jump, and the 26 bits are for the address. So here's your example. So opcode is 2, and we just are using a very small amount of the 26 bits. But this would just be sign extended, right, with the zeros. Right. So we have these different conditional statements that we can have in our code. We can branch if where 2 registers are not equal, branch if 2 registers are equal, or we can just unconditionally jump. Okay. So we have these 2 different formats. I-type is for if we need to compare 2 registers, so that's branch not equal, branch equal. And then jump is for there's no condition. And we have a wider range of addresses that we can reach because we don't have to specify the two registers. So one thing that we have to consider is that addresses are not 32 bits, right? So 16 bits is not enough to reach all of the addresses because the actual addresses are 32 bits, and even 26 bits, not enough. So for large programs, this could be a limitation, but we'll find that most branches are local. So even though it could be a limitation, most branches are only going around 16 instructions away. So your loops are not very large, if statements are not very large, right? Procedures are where you're going to be jumping further. But even then, we don't have to be able to reach the entirety of the code space. Most programs are not going to be 4 gigabytes large. But, well, next slide is the best. But for PC, we are doing this relative addressing because most branches are local. So we're going to treat the 16-bit number as an offset to the PC register, right? And the target address just becomes PC, which is our current instruction pointing towards the branch. But one thing to keep in mind is by the time we add the offset, PC is also incremented by 4. So it points to the instruction just after the branch, and then we add the offset. And we can save some space because we know that we're going to be word aligned, we don't have to specify the last 2 bits. But they're always going to be 0. So that's why we multiply the offset by 4. Okay. So jump is a little bit different. Rather than being a strict offset, it kind of just replaces the last few bits of the PC. So it keeps the 4 most significant bits of PC. And then for the other 28, the first 2, again, are always 0. And then the next 26, we're replacing with these bits of this address. So it's not an add, it's a bit replacement. But it is still relative because we're keeping the top 4 bits of PC. So this is probably one of the things that most students would forget because we don't use jump a lot. We use branch not equal, branch equal quite a lot. But when we go and look at the data path, we need to remember that it is this bits replacement and not an add. So, but what if we need to reach somewhere that is too far for the 16-bit offset? What the assembler will do is it will rewrite the code. So it turns the branch into an unconditional jump. Because the unconditional jump, we can go further. And then it just inverts the branch condition to decide whether to skip the jump or not. Right, so here's the example. If we have this branch equal, and we're comparing these 2 registers, and we want to go to some label L1, but our 16 bits immediate is not large enough to reach L1, it will convert this into these 2 instructions. It'll flip the condition and branch not equal and skip the jump if we shouldn't have gone to L1. But if they are equal, which was this condition, now we go to the unconditional jump and we can reach L1. So that's one way that the compiler or the assembler will rewrite the code in order to make sure that you can still reach if something is not reachable by the 16 bits. Any questions on this so far? Yeah.
Yeah, does the compiler have to check every single branch to make sure that each jump is within the 16 bits?
Yeah.
During it? Okay.
Yeah.
And that's just a compromise it has to take while it,
Yeah, it's not a huge deal because most of the time, like we mentioned, because we do relative branching and most of our branches are for loops or if statements, the only time it's really a consideration is where am I going to put all my procedures? Because the procedures are the ones that are going to be further away. And that's just a matter of reorganizing the code. Like if you find that you can't reach this procedure, you can just move it up or something like that.
right? Okay.
Alright, so this is your first checkpoint. We just want to make sure that we are able to convert all of these from binary to the MIPS instruction or vice versa. This is in your homework and this will for sure show up on your exam. And your code for today is 544. Okay. Is anyone still thinking about this? All right. So you guys keep changing your answers. I with that, All right. So there are two popular answers. We're not at the threshold, but what you should do is talk to the people around you and walk through which one of these that you chose or which one that you did choose and how you got there. And let's see if we can move more towards the correct answer.
It's really more, I printed out the worksheet and the 1 and 0 writing it down. I think that's trying to trick us up. Immediate ads. I'm thinking the first instructional office. The next five. That 0 RS. And then Brad our team destination, so. I got 8 for the RS. So RS would actually be the second thing after the destination. It can't be a register. I'm thinking it's early in the morning. Will scram. If I'm writing it down.
Okay, do change your answer if you were to change. Did have movement towards the right answer. So let's do this together. First thing is opcode is always the first how many bits?
6
6. So I'm just gonna draw a line here. So this, if I convert it to text, which is what your mid sheet is in, this is 8. Right? So 8, if we look it up, it is indeed at immediate. And then because now we know it's the immediate instruction type, the next how many bits are what I should look at? 5 bits. So like this. And this is RS, right? And this is 8, right? So that is T0. And then the next 5 bits are RT. And this is 16. So that is S0. Now we can just double check that the immediate is right. So this is 32 plus 2, 34. So the one thing that we just want to make sure here is that if for add I, again, if we look at the mid sheet, it tells us that it's RT equals RS plus the sign extended immediate, right? And the first field here is the destination. So this is why S0 should be here and not here, and T0 should be here and not here. Because we always have our destination and then our 2 operands, so this is A. But it is very common to have this mistake between A and B. But hopefully we get the mistake out here and you guys can get this right on the exam. All right. Oh, this is just going over it, splitting it up, right? So 8, 8, 16, 34, add I, C0, and then S0. So what's add I, S0, T0, 34. Correct. So here is one of the pieces that we need to go over for your homework. So it's our target addressing example. So we have this branch not equal instruction that wants to go to the label exit down here. If the two registers are not equal, and we need to figure out what is the immediate that should go here in order to accomplish this. So what happens when we execute this branch not equal? We have PC, right? And what happens to PC? It's incremented by 4 first, right? And now let's assume that the two registers are not equal. And we need to change PC from this to this. What is our immediate that we need? Needs to increase by how much? Yes,
The immediate is 16,
here.
32.
So this is my PC after I increment it, right? And the immediate is going to be added to it, but there's something else that happens to the immediate before that. I need to add 8. What happens to the immediate before it gets added? What are the last 2 bits of every single instruction address? So what happens because I don't want to put that into my instruction? My immediate gets left shifted or multiplied by 4, right? So I need to add 8, right? But I need to divide 8 by 4 before I put it into this field, because it will be multiplied by 4. So really what you can think of this as is if I'm going forward, I'm going to increment PC by 1 instruction here, and then I just need to go 1, 2 more instructions down. So the immediate should be a 2. But the other example that we have here is this jump. And the jump, it does do relative addressing, right? But it doesn't just add, it's replacing 28 bits of PC. So I need to go from here. And again, it's going to be PC plus 4. But PC plus 4 is not going to change the top 4 bits of PC, right? It just changes the bottom parts. So it doesn't really change what I'm going to put here. But I need to make sure that the bottom bits become the equivalent to make this as my new PC address. And we just have to remember that it is left shifted by 4. And the reason that it is just 20,000, because it does get left shifted by 2, so multiplied by 4. And this 80,000 means that the top 4 bits of PC are all zeros. Right? So it just keeps this all zeros and then replaces the rest. That's how we can do the jump. So this is one of your questions on your homework, right? It gives you a small like code example and it's asking you what the immediate should be replaced with.
Sorry, could you go over again how you got 20,000 for that box?
Okay, so top 4 bits of PC stay the same. Okay, so our PC is currently this. Right? Top 4 bits of this as a 32 bits binary number are 4 zeros, right? And then we need to replace the bottom 28 bits with what we put here times 4. So all 0 So we need 80,000, so let's divide 80,000 by 4, because we know that we're gonna multiply it by 4. And we put 20,000 here. And then when we append these 4 zeros, it doesn't change it anymore. Right? Okay. So here we just have a summary of the different addressing modes in MIPS. So we have the immediate addressing, and we can also specify different registers. And we can also have this base address of a register plus the immediate of the immediate field. And we also have PC relative addressing by having the PC address, but it's PC plus 4, because we always increment PC by 4. That's one of our first steps. And then add the relative address to it. And we also have this pseudo indirect addressing, where we're keeping the top 4 bits of PC and replacing the bottom 28 bits. So out of all of these, this one is probably the most forgotten. Just make sure that you remember what this is doing for jumps. Right. But the last thing are procedures. So procedures or subroutines are needed for structured programming to kind of split things up into smaller functions, and then you would use those functions as helper functions, things like that. So in order to call a procedure, we have to follow certain steps. So we first need to place the parameters needed for it in the registers, where the procedure that we are calling, or we'll call it the callee, can access them. Then we need to transfer control to that procedure, which is basically incrementing or branching PC to then point to the first instruction in that procedure. Then we need to acquire storage resources needed for this procedure. This would be decrementing the stack pointer, because we add to the top of the stack if we need more memory. Then we can perform the procedure's operations, place the results back into the register file so that the caller can access them when we go back to where the caller was. And we return control to the point of origin or the instruction right after where we called the procedure. Make sense? All right. So here are the registers that we are using for procedure callup. So A0 through A3, these are your argument registers. This is used to pass our parameters. So like the base address of an array, or just if you have, maybe you don't have an array, you just have some variables. You have 4 registers to do that. And then V0 and V1 are used to return values. So you can have multiple returns. And then the register RA is to return, it's the return address to return to where you called the procedure. But more specifically, it's the instruction right after the call, it's the procedure. All right. So to transfer control to the callee, we use this instruction jump and link. And the jump and link does 2 things. It saves our return address, which is PC plus 4, into the return register. So we know where to go to when we finish the instruction. And we also jump to the address of the procedure. And then for returning the control to the caller, we use jump register. And we already have the address of where we need to go back in the RA register. And it's just copying that address into PC. So basically, when you want to call a procedure, you have jump and link, and then the instruction right after is what you would be returning to. when you finish the procedure call. Alright. So any registers needed by the caller must be restored to the values that they contained before the procedure was invoked, because we expect our register file to be the same as when we called the procedure. So if the procedure needs to use any registers, it needs to save what is currently in those registers to the stack, or in this case, it's the stack is memory, right? So it is a last in, first out, and the stack pointer points to the most recently allocated address in the stack to show where the next procedure should place the registers to be spilled, or where old register values are found. And the stack pointer is adjusted by one word for each register that is saved or restored. So if you need to save one register into the stack because your procedure just needs to use one register, you decrement the stack pointer by 4, do a store word of that register to the stack pointer now, and then you can load word, do whatever you need to use that register. And before you do the jump register to return to the callee, you load word that register value that you stored to the top of the stack back into the register and increment the stack pointer to say that it was removed. And the reason that we decrement to add things is that we grow from higher addresses to lower addresses. So we go up, we don't go down. So here's our example. So a leaf procedure is just a procedure that doesn't call another procedure. It's just the last one. So our arguments, we have 4 arguments, G, H, I, and J. Those will be stored in A0 through 3, right? And our return F is going to go into S0. And well, no. So the result is going to go into B0. But we need to save it into B0. We're going to operate it as S0 first. So here is our MIPS for this. So we need a register for this F, right? So the first thing that we do is we decrement the stack pointer by 4 so that we make space to save the register that we want to use. So the register that we want to use is this S0 register. So we're going to store word, the contents of it, to the stack pointer. Then we're going to use the temporary registers, which are not guaranteed to be preserved because they are the temporary registers, to do G plus H and I plus J. Now we have T0, T1, and then we're going to subtract G plus H by I plus J and put that into the register S0 that we are using for F. And then to make sure that our result is stored, we are going to add into V0, which is the return register, our result, which is in S0 and 0. And then we're going to restore the previous value of S0, load word, stack pointer into S0, and then increment stack pointer to now point to the new top of the stack and return. Any question here? All right. So we have also non-leaf procedures. So procedures that call other procedures. These are nested calls. So you have A that's going to call B, and then B calls C, and then C is the leaf. C finishes, you return to B, then you return to A. Right? So we just follow the same procedure that we did before, right? So the caller needs to save onto the stack its return address, because you only have that one return address registered. So if you are a procedure and you need to remember where you needed to go to return, before you call another procedure, you have to put the return address onto the stack. And you also need to put any of your arguments and temporaries that are going to be needed after you call the next procedure. And then once the procedure that you called returns to you, it will restore all of these from the stack after the call. Right. So here is our anomaly procedure example. So this is a recursive code, so it's calling itself, right? So here is the beginning of it. We need two things. We need to store the return address so that we know where to go. And we're also saving the argument n. And then we're going to see if we need to do the return here or recursively call and do the return here. So we're going to do this test for the if statements with set less than immediates. And again, the set less than immediates is very useful here because a lot of the times we'll have something like this where it's not two registers being compared. Then we're going to branch if they're equal. So if this is not true, we will branch to L1, which is down here. But if this is true, that means that this was not true, right? We'll do this part, which is our return. This one. But L1 is our recursive call, right? So if we do the recursive call, we need to decrement n, jump n length, right? And then when we come back, we're going to restore all of these items and return to the previous one. It's going to restore, keep going until we get back to here. And when we're on the last one, we have the just return. Right? So these recursive codes are a little bit more complicated. Right? The last thing that we need to cover for your homework is arrays versus pointers. So we have array indexing, which is going to index by the element size, and we're basically have the base address, and we're going to add the offset to that base address as array indexing. And then pointers correspond directly to the memory address. So rather than keeping that base address, we're going to continue to just modify the direct address, and we won't use the immediates. So here is an array version of looping through an array. So first thing is I is 0, and we're going to multiply our, what is in T1? T1, so T0 is I, so we're going to multiply our current element that we want to address by 4, and that's going to be our offset. So T1 is the offset. Then we're going to add to the base address A0 the offset to get the address that we want to look at. And we're going to store into that address 0, because all we're doing here is zeroing out the array. Then we're going to increment I, set on less than, branch if we're not at the end. Okay. So this is what we've seen so far. This was the same example that we had before. For the pointer, we're going to do it a little bit differently. So we have the base address A. And we also have the size of the array in A1. So what we're doing here with these two adds is getting the total size of the array. Because we have the number, but we need to multiply it by 4 to get the total size in terms of address space. Then we add the total size in address space to the base address. And now T2, that's the end of the array. Or more specifically, it points to the next address in memory that is not the array, right? Then our loop, we simply are storing 0 to the current address, right? And then we're going to increment the address directly by 4 to get to the next address. Now we're going to check, are we at the end? If we're not at the end, then store a 0, increment again. And the key here is that if we look at these two examples,
On the previous,
it's right here.
okay. There was the add, I believe. If you had I equals 0, if you added I to itself, would that actually increment it?
Yeah, well, I mean, if it's 0, you want to access the first one. So it shouldn't increment, right? But when you increment I, okay, because you increment I down here.
Oh.
So now I becomes 1. And then when you get here, 1 plus 1 is 2, 2 plus 2 is 1. Anything else? Okay. So the key here, between the difference between array addressing and pointer addressing is with array addressing, we have, oh, and the other thing that's changed between the previous slide and this is rather than add structure twice, we are just shifting by 2. So that is also going to accomplish our times 4, right? So it's a little bit more complex. But the key between here and here is for our loop with the array addressing, we have 1, 2, 3, 4, 5, 6 instructions. For our loop with pointer addressing, we have 1, 2, 3, 4 instructions. So we have a third less instructions per iteration of the loop. So this will be faster in terms of implementation than this. So the pointer version reduces the total number of instructions per iteration from 6 to 4. And one thing that you can keep in mind is that almost all optimizing compilers will generate the pointer code. So even if you write code in the array indexing form like this, the compiler will turn it into this. So if you like coding like this, you can continue coding like this. You don't have to deal with the pointers if you don't like dealing with the pointers in your high level code. Compiler will optimize for you. What the compiler will not optimize for you, and we'll see on Friday, is a bad algorithm. So the compiler can help you in many ways, but if you have a bad algorithm, bad memory management, the compiler cannot do everything for you. So you do have the reading, the end of chapter 3 for Friday. And with this lecture, you should be able to do all of homework 1.
Just answer anything for the final question on the whole.
Yeah, for the second question, you can answer anything.